This is so how to remove that phobia. Okay. Suppose any phobia, you are the new admitted scholar, or suppose you did your PhD and again you have the phobia to write a papers, or again you have many challenges. So already we have discussed how to remove this phobia. So there are the 2-3 main components. Suppose you know those components. For example, that is tool. Okay. So what is exactly that tool? It depends upon your interest. So suppose you will choose any one research area, then you will find out some literature related to that topic. Then in that paper there are some tools. Authors have written those tools. Clear? So we will discuss how to read a particular paper. अभी तक हमने देखा है कि भाई पेपर क्या होता है, पेपर के अंदर कंपोनेंट क्या क्या होते हैं. सपोज वी वांट टू राइट ए पेपर, व्हाट इज द साइज ऑफ द पेपर and what are the size of each component. For example, we say abstract, for example we say conclusion, for example we say introduction, related work, proposed work, result and discussion. So suppose there are the 2 and 3 category of the research paper. So first category is survey paper, second category is review paper, third category is research article. Okay, so one is the survey paper, one is the review paper, one is the research article. Again there are the 2-3 category where you can publish. You can publish your paper in a magazine, you can publish your paper in conference, you can publish your paper in journal. Again there are the many category of the journal. Only peer review journal, which is having only ISSN number, ISSN number. Second, there is a UGC listed, अभी तो UGC ने मना कर दिया है, UGC केयर जर्नल, then Scopus जर्नल, ESCI जर्नल, ओके, फिर SCI जर्नल, फिर SCI जर्नल, understand? So these are the different category of the journal. Then in IEEE there is a transactions. Okay. So this is the list of the journals and transaction IEEE. So if we say the in science or computer science, so IEEE is number 1. ACM IEEE. In journal, nature is number 1. Suppose you will publish your paper in nature. So the impact factor of that it may be 50. Suppose it is a journal related to medical or related to chemistry, physics, biotech, so impact factor may be 50. But in general, our computer science, the maximum impact factor is 10 or 20. Understand? So what is the impact factor? Anyone can tell about what is exactly impact factor?
How the paper is dealing the over
ठीक है. So suppose you are the researcher or already you have completed your PhD, so your target is impact factor. suppose it is low, so it is average journal. Suppose it is medium, so it is good journal. Suppose it is very high, it is very 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 excellent journal. Okay, so in your computer science, electronics, electrical, so it is IEEE. Suppose you will publish one paper in IEEE, then your PhD will be complete. तुरंत कंप्लीट हो जाएगी. जिस दिन आएगा उस दिन अगले दिन आपका सुपरवाइजर कह देगा आप जाइए. आप 2 लिख लेते हैं तो फिर आपको शाबाशी भी देगा. अंडरस्टैंड? 3 लिख लेते हैं तो समझ लीजिए कि माला वाला पड़ेगी आपको. So this is the value of the IEEE transaction. When you will go outside with 3 or 2 IEEE transaction, तो आप IIT, सेंट्रल यूनिवर्सिटी, IIT की बात नहीं कर रहा मैं, ठीक है, that is the different one. बट यहाँ आपकी जॉब अगले दिन लग जाएगी 100%. Suppose you have 2-3 IEEE transaction paper. Suppose you have 5 or 4 SCI journal which is done during your PhD, तो भी आपकी जॉब 100% लगेगा. ठीक है. Suppose you have one only Scopus paper, you have the 2-3 peer review paper, तो फिर आपको एडिशनल वर्क करना पड़ेगा, थोड़ा एफर्ट करना पड़ेगा जॉब के लिए. So that is the credential. Suppose you have IEEE transaction, SCI journals, so you are the visible in domain. बहुत सारे PhD कर रहे हैं, बहुत सारे thesis submit कर रहे हैं. But suppose you have and you did your work and it is going to publish in IEEE or SCI journal which is having the good impact factor, then you are the visible and out of the crowd. Clear हो गया? अगर आप ऐसा करते तो आप बाहर हो एकदम. फिर आपको ना किसी सोर्स की जरूरत है, ना सिफारिश की जरूरत है, आपका सिलेक्शन 100% होना ही होना है. So this is the value of your work, this is the value of your papers. Understand? Is it clear? So same way ये पता चल गया कि आपका जो कैटेगरी है वो क्या है. Suppose it is a conference paper, so it may be 4-5 page maximum. Suppose it is a review paper, it may be 10 to 20 pages. Review means you will provide, suppose you are the just learner or starter of that area. आप अभी अभी उस एरिया में आए हैं, एरिया तो बहुत पहले से चल रहा है, बट यू आर कमिंग एट दिस पॉइंट.
Sir, mine is 16 pages. My conference paper was 16 pages, sir.
16 नहीं, 16 पेज का था.
It got best paper award also.
कौन सा पब्लिशर था?
Elsewhere. Springer.
एल्सवेयर में लिमिट नहीं होती है, स्प्रिंगर में भी लिमिट होती है, और आपका IEEE में भी लिमिट होती है 6 पेज 7 पेज, है ना. अदरवाइज यू कैन एक्सटेंड बट विद एक्स्ट्रा पेमेंट. अंडरस्टैंड? उन्होंने पैसा लिया होगा आपसे, लिया नहीं, ये तो बहुत अच्छा है. Some format having like that size, some having the double size. For example, 1 column, second column. अगर ये 6 पेज का ऑटोमेटिक 12 पेज का बन जाएगा. अंडरस्टैंड? तो उस हिसाब से इनका 16 पेज का होगा. इट मीन सपोज इट विल कन्वर्ट इनटू IEEE, इट विल बी मैक्सिमम 8 पेज. IEEE का 8 पेज, बाकी जनरल का 16 पेज हो जाएगा ऑटोमेटिक. सो ऑलरेडी देयर इज ए लिमिट इन IEEE ट्रांजैक्शन आल्सो, इट इज 8 और 12 पेज. सपोज देयर इज ए एक्स्ट्रा पेज, देन इट इज पेड बाय यू. ओके. सेम वे कॉन्फ्रेंस और बहुत सारी चीजें भी एक्स्ट्रा में ये कहते हैं. तो कभी कभी हम एक्स्ट्रा कर देते हैं उसमें, बट इट मे बी सपोज ऑर्गेनाइजर प्रोवाइड द सेम थिंग और पब्लिशर प्रोवाइड द नो लिमिटेशन, देन यू कैन पब्लिश. इन जनरल इट इज ए 6, 7, 8 पेज डबल कॉलम, और इन सिंगल कॉलम इट इज ए 10 to 15 पेज. नो इशू. ओके. देन देयर इज ए सर्वे पेपर. एक तो हो गया रिव्यू. रिव्यू मीन्स you will provide the only overview of that subject. जैसे आप किस एरिया में काम कर रहे हैं?
Social network.
सोशल नेटवर्क. आप किस में काम किया है?
पर्सनल ऑथेंटिकेशन.
आपने किस में काम किया है?
इंट्रूजन डिटेक्शन.
आपने?
सबऑर्डिनेट डिटेक्शन.
आपने?
Sir, intrusion detection.
आपने?
Sir, food safety detection.
आपका?
इंटेलिजेंट पैकेजिंग
आपका रूम का प्रॉब्लम सॉल्व हो गया? अच्छा, आज बात करना मेरे से. So already you know you have the one research area. So suppose you will pay near about 6 month 1 year और आपको बहुत सारी चीजें मिले, नए नए की टर्म्स आपके लिए जो है. So you will compile those key terms and you just try to create one paper. Okay, the answer will be related to what ये चीज क्या है, बस इतना ही आंसर उसके अंदर है. Suppose I say what is the intrusion detection, what are the different techniques, okay, what are the different model, what are the different architecture, what are the different component, what are इनका आंसर मिलेगा उसमें. So abstract में भी what का आंसर, conclusion में भी what का आंसर, related work में भी what का आंसर. So it is called review paper, review not survey. समझ में आ गया? रिव्यू का मतलब है ओवरव्यू, केवल उस सब्जेक्ट का बताया गया. इट इज लाइक ए बुक चैप्टर, इट इज लाइक ए जनरल इंफॉर्मेशन अबाउट सब्जेक्ट. ठीक है. सेकंड पेपर इज योर सर्वे पेपर. सो व्हाट इज द इम्पैक्ट फैक्टर ऑफ द सर्वे पेपर? कैन यू टेल मी एनीवन? सपोज आप सर्वे पेपर छापना चाहते हैं किसी जर्नल में, तो व्हाट इज द मैक्सिमम इम्पैक्ट फैक्टर इन कंप्यूटर साइंस रिलेटेड टू सर्वे?
5 to 6.
5 to 6. कोई आइडिया?
Maybe 20 also.
20. और बताइए.
So about 20 hours.
About 20. किसी को आइडिया? So there is a IEEE survey. Understand? IEEE survey is one transaction. So impact factor is near about 21. है ना? 21 है उसका. It means suppose you will write a survey paper in good manner. So it is not a task of the one scholar. So it required 1, 2, 3 scholar minimum. Okay, and you will write the all things in that paper from scratch to till date. आपने लिया 20 साल पुराना. So suppose you are working in authentication. So what is the authentication before 20 year? Then in 19 year. Then 18 year, then 17 year, then 16 year, then 15 year, then 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. आइए आइए सर आइए. So this is the time period. You just wait for 2 minutes, sir. I will come to. So further we will discuss how to read the paper after this session. Okay. Now it is clear what is the type of the papers, what is exactly survey paper, what is exactly review paper. Then we will discuss research article. Already it is an example of the research paper. Then we will discuss that time. Clear?
Yes.
So thank you. So most welcome to Dr. Indivar sir. Okay. So he will take the next lecture. And I think you will be ready for some mathematics also, cryptography. Thank you. ये बंद कर दीजिए सर, कैसे आइए. मैसेज डाल दीजिए, आ जाएगी सभी जिसको आने. टी ब्रेक कब होगा हमारा?
is my distinct pleasure to introduce our speaker for session 7 of the Advanced Cybersecurity Faculty Development Program. Today we have the honor of welcoming Dr. Indivar Gupta, a visionary scientist whose exemplary career spans cutting-edge research in cryptography, number theory, and high-performance computing. Currently, as Scientist G, he spearheads the asymmetric key analysis group, driving innovative research that safeguards our digital world. Beyond his significant contributions in the lab, Dr. Gupta is a dedicated academician who has mentored numerous PhD and MTech students across leading institutions, nurturing the next generation of cybersecurity experts. His prolific output of over 45 research papers and his active engagement in international scientific forums underscores his commitment to advancing our understanding of cybersecurity challenges. Today, Dr. Gupta will share his insights on safeguarding data in a quantum-enabled world. Please join me in welcoming Dr. Indivar Gupta to the dais.
ये लगा देना पहले चंद्रेश, पहले सर्कल लगा दे।
Good morning to all of you.
Good morning, sir.
अजय सर,
Everybody.
इधर आ जाओ।
So how many you are familiar about this cryptography?
Not much, little bit.
Little bit. So all are from computer science background or mathematics background?
I'm from electronics and communication.
Electronics and communication.
So, computer science.
Computer science.
सारी ले आएंगे। है पढ़ना, इधर ला। पढ़ना।
Hello. Yes.
सर भी आ गए, लो। हाँ, अजय सर आ गए।
Hello sir. Good morning.
कैसे हैं आप?
So what do you understand about cyber security? Do you know about what is the cyber security? So we have a lot of system connected through wire or wireless network. Communication is going through that network and you have to provide your data. So all the data is available on the cyber space, and you have to provide the security. So cryptography is one of the important aspect to provide the security. Okay. So just for the basic definition, suppose you want to do any digital communication, so what you do here? Whatever you have a data, fax, speech, you send input, do this coding, then comparison, and then encryption technique, right? So, and then after that you can use stenography and then error correcting coding, and then after that we transfer the right? So here the encryption or the role of cryptography comes here, right? So what do you mean by cryptography? Like we have to design certain algorithms, protocols to provide the authentication, integrity, confidentiality, non-reputation. It's basic understanding, right? So you have to design certain kind of algorithms which we can use to provide the data security data. Okay? So now we are coming to the cryptography. So in the cryptography we can divide into two parts. That is one classical or conventional cryptography and other is quantum cryptography. Right? So in classical and conventional cryptography, in the classical and conventional cryptography, like traditional cryptography, we are using block cipher, stream cipher, then public key like RSA, elliptic curve discrete help block problems, hash function. So these are all we use call it classical. So like AES, we are talking about AES or DES, right? Hash function, subfamily, MD5. So all of this we use to call the that is a classical part. Now here like the post quantum. So suppose we have a quantum computer, then you have to define certain schemes which are secure against which are secure when we will have a quantum computer. So all these schemes initially, that classical scheme has been designed based on the availability of computational resources. So now the computational resources is growing exponentially, and then there is a chance to have a proper quantum computer with a large number of qubits. So accordingly we have to define our protocol. Okay? Cryptographic protocol. So now we are talking about the quantum cryptography itself. So when we use actually quantum computer to design a cryptographic protocol, that is called the quantum cryptography. So there is a difference like post quantum and quantum. So post quantum is actually the classical cryptography only, but we have to design in a certain manner so that we can use that schemes. We can use that scheme even if we have a quantum computer. So we have to enhance the mathematical, in the secret key we have to enhance the key size, and then the public key we have to change the mathematical background, mathematical problems and other things. So you know, I think when quantum computer talk might have been covered. So I will discuss 2-3 slides on that only, because this that quantum part is not a scope of this talk. So what is quantum computer? You know that computer that use basic particles and quantum machine principle in preventing for this, especially for to do the computational tasks and to store the data. So when we use this quantum principle, that is quantum mechanics principle for the computational tasks, so then that is called the quantum computer. Quantum cryptography, that is cryptographic application using quantum computer. So that quantum key distribution, quantum coin flipping, etc. This is a part of the quantum cryptography. So we use actually the quantum computer to design this protocol. So you have like seen now a lot of research has been done in the area of quantum computer. The theory itself, the theoretical foundation of quantum computer has started in the early 90s. So 1990 to 1980, that lot of theoretical work has been done. But the special things that goes to that Paul A. Benioff, they have introduced the quantum Turing machine, just like a computer. We have the Turing machine concept and then finite state automata and other things. So they have introduced the quantum Turing machine. Then in 1994, the important protocol that quantum key distribution, they have that Charles and Benioff and that Vissard applied the quantum theory to demonstrate the quantum key distribution. So this is the from the year 1984, lot of cryptographic work has been done using this quantum principle. So, and then the concept of quantum circuit came in 1986. Most important concept, that is 1994, Singh gave the quantum algorithm to solve the hidden subgroup problem. At the same time, the Petersdorf introduced the this concept of the using this quantum computer, that is called family of mathematical problem, that is solving the factorization problem. So this is the most important part here. So because the RSA crypto system is based on the factorization, and in 1994 he introduced he showed that theoretically. That time it was that quantum computer is not that. They said that if we have a quantum computer, then it can be used to solve the certain mathematical problem. And then 1998, the concept of the this QCL, that quantum language, came. Okay, and again, and then in 1998 itself, MIT developed the 2-qubit quantum computer using NMR, that is nuclear magnetic resonance. So this is the important theory, important. And then 2001 again, then 7-qubit using this NMR concept introduced. Now since last 10 years, in this area, the development of computing, lot of work has been done. So you can see in the the current stage in 2004, researcher achieved the first conventional interaction between two whole spin qubit. IBM quantum Huron chip are released in 2023. So this is contain 133 qubit, and then the IBM unveiled the 1121 qubit processor called conduit processor. So that way, now that in last 10 years, we have a lot of work has been done. So you can see here from the theory to now the current. So we have initially we have started a theoretic foundation, now we have a quantum chip. So whole journey you can see but the last after this 2017 and 2017 to 2024, that lot of work has been done. So we have a certain kind of quantum computer that is called superconductive quantum computer, gate-based quantum computer, ion trap-based quantum computer, then photonic-based quantum computer, quantum annihilator, topological quantum computer, and NMR-based quantum computer. You can see here that is commercially available things like this unity computing, that is launched 9-qubit recently, IBM system 1, D-wave advantage, that is ion trap based, ion cube, spin cube. So these are all commercially available, and the IBM also provides cloud-based service, and this D-wave is also providing the cloud-based service. So traditionally, what is exactly if we compare the classical computer and quantum computer? So in the quantum computer, the calculations computations are done in the qubit, which can be represented as 0 and 1 at the same time. Okay, so simultaneously they can represent the 0 and 1. And the classical, you know that what we do, the computation are done with the transistors which are either 0 or 1. So since we can represent it simultaneously, so then we can represent a 2-bit at a time. In 1 qubit, so power increase exponentially. So if now the lot of quantum simulator is available in the market, and then if suppose they have a 40 qubit quantum simulator and they want to make it 41 Q1, 41 bit, 42 bit. So then they have to do the resource. They have to double the resource every time. So power increase exponentially in the proportional number of qubit. But here the power is increasing linearly. Okay. In the quantum computer, it has a high error rate and need to be kept in cryptogenic temperature, that is -273 temperature. In the classical computer had low error rate. So this is a certain advantage of classical decision. And then you can see the other qubit. They use the quantum gate. Here we have a certain advantage, like quantum qubit and superposition. Main concept in the quantum computer, quantum qubit and superposition. We use entanglement, interference, quantum gate, quantum algorithms, then error correction, and quantum superposition. So these are the main important things, important concept in the quantum computer. So now we are coming to the quantum cryptography. So as I said in the 1994, that quantum key distribution protocol introduced. So to exchange the key, they have given the quantum key distribution protocol. BBB 84 is an important quantum key distribution protocol. Then E91 quantum, and this is available, E91 protocol. Now we have a random generator based on quantum phenomena. So like quantum random generator, and we also that scheme has also been given for the quantum secret sharing. Like other in cryptography, we have a secret sharing. So quantum secret sharing, quantum computer, using the quantum computer, we have a scheme called quantum secret sharing. And actually, that the first that demonstration is done in 2001 itself. So in India also, you can see that we have a national quantum mission, and government is funding to do this quantum research and development of quantum technology in a drastical manner. And in DRDO and this IIIT Delhi organized the demonstration, this quantum key distribution, demo of the quantum key distribution. DRDO and IIT Delhi organized this demonstration in the various quantum communication technology. So you can see the news. So now in India also we have this quantum distribution, key distribution technology. ISRO, see the ISRO makes a breakthrough demonstration of free space quantum key distribution. So you, because I don't know whether you people understand the free space or not. Means without any medium, free space quantum technology, so no wire connectivity is there from one station to another station. They demonstrate this quantum key distribution technology. So again, this ISRO in India plan to launching this quantum satellite in 2-3 years. Then in Chennai, I think that quantum security law launched in Chennai. So that PSA, Principal Scientific Advisor, is there. Is launching this quantum security lab in Chennai. So this is all about the just because we have given the gist of what is quantum computer and how that lot of things has been done in India as well, in addition to globally. Global research in the and IBM actually have a lot of this quantum infrastructure currently. So now we are coming to the public key cryptography, and then we will discuss that how this quantum computer that making breakthrough this in this direction in the area of public key cryptography. So in case of symmetric key cryptography, as I discussed, suppose like you are using the current AES, and when we will have an actual quantum computer, like a lot of with actual quantum computer means large number of qubits we have in the quantum machine. Then currently, suppose we are using AES 128, then we have a quantum algorithm that can AES 128 means what it meaning. AES 128, what it exactly meaning is that it has a complexity, brute force complexity of 2 to the power 128. And when we will have a quantum computer, then we have a quantum algorithm that is called global search algorithm that can be used to solve this used to solve that is by square root of that. So that is 2 to the power 64. So in that case we have to change the little bit AES, and what we can do, like we can increase the size and we can increase the block size and we can increase the key size. So suppose we want to provide a 128-bit security only, then we have to use the AES 256. Okay, so even we will have this global search algorithm, and then complexity will be reduced to square root of that, still it will be secure. So if you want to provide the AES 256-bit security, then what we have to do, if you use the 512-bit, then after this quantum computer have, then you will have the same level of security. So in symmetric key cryptography, most of the algorithm, just you have to twist them, and you can use added, only you have to increase the block size and key size. And you have to check also some circuit depth and other things. In the public key cryptography, what is the important, because we have to use the mathematical problems which are being used to design public key cryptography. So what problems we are using? We are using integer factorization. So RSA is basically based on integer factorization problem. So when that integer factorization problem, when we have this quantum computer, then Peter's whole algorithm can use to solve the integer factorization problem in polynomial time. Okay, so that means currently the whatever algorithm we have in the classical computer, this is all sub-exponential algorithm. So here, for understanding of public key cryptography, some part of complexity theory I have to introduce. Okay, so you will discuss about little bit about the complexity, and I will tell that how this complexity of different RSA algorithm, other things is exponential, and then some mathematical problem which are sub-exponential, some problem is exponential, and then what will happen when we will have a quantum computer. So in this, by next talk, we will discuss all these concepts. So you know what is public key cryptography?
Yes, sir.
I think everyone knowing this, what is the public key cryptography. Okay. So it's introduced in the just one or two slide. It was done by first it is introduced by Diffie and Hellman and Barclay. That is in mid-1970s. So you know that what is each user has pair of key that is known as a private key and public key. Everyone has access of public key and a private key. Information is can be accessed by only the owner. And this public key cryptography depends on the computational hard problem. So that I am going to discuss. That prevents the inverting the public map. And computing the private key from public key has to be interactable. Okay. So you know the concept, how this works. Okay. Here. So like suppose you want to exchange your key, so you can use the public key cryptography. If you want to encrypt the message, so what you have to do, you have to use the your public key to encrypt the message, that receiver public key to encrypt the message, and receiver can decrypt from his secret key. Okay. So here, if you want to send a message to Alice, so what you have to do, Alice will have its own public key and private key. So suppose Bob wants to send some message, so Bob will use public key of Alice, and Alice will decrypt the message using her own private key. Okay. So what is in mathematically, what is that? Like it is a public key cryptography is a pair of families of that is called encryption algorithm and decryption algorithm, and then that encryption algorithm map from message space to the cipher space, and then the decryption algorithm map from the cipher space to message space. Okay. So for every key, so that is key is basically key space. Okay, key is key space. So for the every k in key space, dk is inverse of ek and vice versa. Okay, for every k in key space, that and m in message space and c is in a ciphertext space, algorithm ek and dk are easy to compute. So what is this meaning? Like any public key algorithm, that encryption and decryption has to be what? Easy. Easy means we should have an efficient algorithm for encryption and decryption. So means encryption and decryption should be in the polynomial time. Okay. And then here, for almost every k, each easily compute algorithm equivalent in dk is computationally infeasible to derive from ek. Okay, so that means like if you have a ciphertext, then you should not able to here computationally, if you have a ciphertext, then it is computationally infeasible to determine the plaintext without knowledge of key. Okay. So we have some advantage and disadvantage of this public key and private public key cryptography. So key security is very good advantage because only private key need to be kept secure. So we can use this public key private key pair for a long time. And then the large in the large network, fewer private key will be required. For the key exchange, in the symmetric key cryptography, what you have to do, we have to exchange the key because the same key has to be used for encryption and decryption. But in the public key cryptography, this concept is not there. So this is the like no key exchange is required. So this is the great advantage. And then using the public key cryptography, we can define a certain protocol like digital signature and many other protocols. So this is the greatest advantage of public key cryptography. Performance-wise, it is slow in general. So you will see like just I will going to tell you another thing. Like for the generally in the all online this application, whether it is banking or email application, for encryption and decryption they are using symmetric key cryptography. But for this your key exchange mechanism and for the signature verification they are using public key cryptography. So because the encryption is little bit slow in comparison to this secret key cryptography or private key cryptography. So like AES, you can see the AES advanced encryption standard algorithm. The encryption is just like suppose you want to encrypt the 128 message. So the complexity is linear in 128 bits. So hardly you can check the entire operation operation manually. How many operations are required to do the to encrypt the 128 bit at a time. But in this particular case, like RSA or other case, we have to do the exponential operation, which is time complexity is qubit, that I will discuss a little bit about it. So that is why this is slightly slow. Okay. You have so in addition of that, we have a lot of we have a very good application like transport layer security, secure that SSL, then signing online documents, hidden key encryption, that pretty good privacy, smart devices, disencryption, blockchain technology, secure boot. We are using the public key cryptography. Okay, so for example, you see this part like SBI online banking. and you check like what kind of certificate they are using. Okay. So just you click on that site and check the security. So you will find here that part, technical details. You can see connection encrypted, TLS, ECDHE, RSA with AES 256, GCM, SAR, this, right?
Yes.
So what is meaning of this? They are using transport layer security 1.2 version. Here elliptic curve Diffie-Hellman key exchange mechanism they are using for key exchange. RSA they are using for signature on the your public key document signature and signature verification, signature generation verification. AES 256 in Galva counter mode they are using for encryption. Okay, and then SAR this 384 they are using for your data integrity. And then see here 256 bit key, that means the encryption means the current encryption is providing 256 bit key. So in any you use the WhatsApp web version, you can check like what kind of protocol they are using, okay, to provide the end-to-end encryption. So they are using TLS 1.3, okay. So this is a new generation of TLS 1.3. Here they have given some freedom to you to use what kind of public key parameter you want to use. So they have mentioned the AES 128 and then SAR 256. Okay, so they are providing 128 bit security, but for the elliptic curve, like for the key exchange mechanism and signature scheme, they are given the freedom. You can use you can set up your own schemes. Similarly, you can see in Gmail. So Gmail also now they have like migrated on transport layer security 1.3 TLS 1.3 version 1.3. Okay. So this is just gist of public key cryptography and this application. Now I am coming to little bit about the complexity. So up to this, do you have any doubt?
You are showing that we have a different security version are using of different applications, the Gmail or WhatsApp. So anybody can use this security level for that other cases also. You know, that much security is they are showing. That is required to show someone is not ethical or unethical like.
No. It has to, because they are showing is their certificate.
Okay. So
they are showing like how you will trust them. Whether suppose you are using Gmail, you know whether it's secure or not.
No, by common person that is not able to understand the other things.
But for common person we don't know. But if you are technical, then you can say like what kind of security they are providing you. Because you should have a confidence on your system. Okay, if you don't have the confidence, then how you will use the online banking? Why we are using this email and other things?
But so this information can be misused by the hackers?
No, because this is a very high level of security. It cannot be used by the hacker.
They are not able to decrypt that.
No, because if no, they can't decrypt. So I will discuss this part why they can't decrypt. So this because they have to take the certificate, they have to publish this in the document. Okay.
So that is 1.2 and 1.3, which one is better? The 1.3 is TLS.
No, TLS 1.3 version is newer version. They have given some flexibility to the users. Okay. So TLS 1.2 they have fixed which algorithm we are using. So now that they have given flexibility that with respect to the public key part, you can use in the WhatsApp they are using elliptic curve only. But like other case, if you want to use some other key exchange mechanism or if you want to use some signature verification algorithm, so they can you can customize it according to your choice.
Sir,
The certificate has to be there because this is one kind of certificate that we are using this. That is why my system is secure.
how to see this page?
Security wise.
Just to open this
web
web page, just open your this
Gmail and WhatsApp.
Firefox. Okay, and then one small
In Google Chrome can't see? Chrome.
Google Chrome, some option is different.
Okay.
How to check this? Its option is there, but it is different. This I have this I have taken on the Firefox. Okay, so
page info में page info
Sir,
हाँ,
जो बात page info आता है
How qubits are different from binary bits?
how
Qubits are different from binary bits.
that is in binary bit we have transistor. It can store either 0 or 1 at a time. But in the qubit, both 0 and bit 1 can be stored simultaneously in superposition. Okay.
for encryption of different bits with a 0 and 1 both.
No, actually, like our classical computer in the transistor, either
0 or 1.
0 or 1.
You can use for 0 for the space and 1 for the mark, something like that.
Hmm?
0 for the space and 1 for the signal will be present in that type of thing you can represent the signal.
No, no, no. It's not like that. I'm not talking about here. In the quantum case, like presently, like information for the store of information or calculation, either we have at a time 1 or 0. But then that time, at a time, we have a, if we have a 1 qubit,
Data size will be required more in that quantum. 0, both the bits are required, 0 and 1.
but for the calculation at a time, you will have a 2 bit. Presently, we are having a 1 bit.
The space will be required more in that to store that part.
So that I have already told, because that when we are using the 1 qubit, 2 qubit, 3 qubit, so the exponential your things like to make the system, the exponential thing will be increased. Okay, because for storing these things, to design these things, you from the 40 qubit to 41 qubit, you have to use the double resources. Okay, you have to use the double resources.
Storage
So-
complexity will increase.
Not storage complexity, because I am talking about when the system is being designed. That time they have to design in a, because every qubit, because we are designing the system. Okay, we are not talking about the presently regarding the this computation or storage. So we are first designing the system. For the designing the system, initially transistors either store 0 or store 1. But when they have a qubit and then multiple qubits, because here you might be knowing that 32-bit architecture, then 64-bit architecture. For that level you have to understand. Okay, for the designing a system, suppose you want to have a quantum simulator, and quantum simulator with 2 qubit or 3 qubit. So that when you design the system, so then every time you have to double your this resources to design the system. So that level, but once we have a system, that time you can use this computation using multiple bits, and you can store data using multiple bits. Okay, but when the designing the system, so this is the problem of designing level. Once we have a system, then that problem is not there.
This is transistor will be replaced by which component? Because transistor is storing either
FPGA.
0 or 1.
Huh. So here that is why I am saying, because quantum computer, they are using different kind of technology. Okay, so either they are using chip, they are using semiconductor, they are using different kind of technology. So how they will replace the transistor, that is different concept. Okay, because the whole technology is different.
So sir, we have different algorithms in publicly cryptography. So can we use these algorithms like RSA in the quantum computers also, or we have to change everything like protocols to systems?
No, so that I will cover. Like in the when we have a quantum computer, so what is the concept of any algorithm, cryptographic algorithm? The concept is we should have an efficient encryption and decryption algorithm. So encryption and decryption algorithm, because this is very efficient, so you don't have to use quantum computer for encryption and decryption. There are polynomial time algorithms, so you don't have to use. Where we use the quantum computer. Now you want to break the system. Okay, for the breaking the system, the complexity is very high. Complexity of the system is very high. So very high. So that current this classical computer cannot solve. Cannot solve means cannot break the system. Okay, using the classical computer. But when we have a quantum computer, where you will have a freedom to work on multiple qubit, then the computation will be fast, and using the quantum algorithm, we can break the system.
So sir, using quantum computer, we can break RSA algorithm or the classical.
So we can break the RSA algorithm.
Using quantum
Computer. We can break the traditional many not only the RSA, other crypto system, classical crypto system, we can break.
So that is the reason why we need the solution, because
So once we have a quantum computer, actual practical quantum computer, in that case, this whole algorithm we have to change. Okay, because we can break the system. Right?
Yes.
But sir, it will be the gateway for the hackers to enter in the traditional system.
Only for this we have security.
So that is what I am saying. Then we have to change the system. So once we will have a quantum computer, then we have to change our algorithm. To what kind of algorithm we should use, which will secure even when the quantum computer will come.
Means we need to increase our.
We need to increase, not only, sometimes we have to change the whole system. Okay, so like in case of symmetric key cryptography, just use only twisting the algorithm and increasing the key size we can buy. Because in case of symmetric key cryptography, currently whatever algorithm we have, global search algorithm, that reducing the complexity just square root. So suppose we have 2 to the power 128 complexity, then square root of that is 2 to the power 64. But in case of public key cryptography, like mathematical problem, like integer factor, once we can solve the integer factorization problem, then we have to use some different mathematical problem which will be secure against the quantum era. Okay?
Sir, how to see this on Firefox?
Pardon?
How to see this info on the Firefox browser?
Just to check that.
Thank you, sir.
Okay. So now we are talking about the little bit about the complexity. So suppose you want to represent a data. Okay, in the classical computer. Suppose you want to say that you want to represent 15. So how this computer will read 15, 1, 5? How many bits you require? 4 bits. Okay, so this is in bit. Suppose you want to represent a hexa. How many bits is required? Only 1 hexa bit. Right? So just we have to take the size of input is here n. Okay, no, suppose we are entering the n. So what is size of it? In bit. So just you have to take the log function. Okay, so what we are doing? 15 log 15 to the base 2 and take the integer value. Okay, so what will come? That is come 4. Clear? So that is basically number of bits required to represent some number. So this is also called the size of that bit. Size of that bit. So that means for storing that number in a computer you need to store 4 bit. Okay. So now, what is running time of algorithm? Now suppose you want to multiply 15 by 15. Okay. So what is running time? You write the algorithm, just you write the small program. What will be the running time of this? Simply. So you represent computer, what will do? It will represent both the number in bits, and then you multiply bit by bit. Okay. So how many that multiplication is required bit by bit? 4 into 4, 16. So to multiply, that means 16 multiplication is required. That is basically the school algorithm. We have a very good algorithm in the literature. Okay. Karan algorithm is there. That complexity reduced. Not that. So now we come. So now what is the complexity of this algorithm, multiplication algorithm? Suppose we have given two numbers. One is n, another is m. So what we have to do? We have done. We have taken the size. So log 2 n, and then size of that number is log 2 m. And total number of multiplication is log 2 n into log 2 m. So this is the complexity. Okay, so suppose n is higher than m, so you can say that order of n square. Done? So this is basically polynomial in size of n, not n, size of n. Because log is basically size. Log n is size of n. So if it is a polynomial in size of n, then we call the polynomial time algorithm. Okay, so I will come to that. So here the running time, you can understand the number of basic operations or steps to execute the algorithm. Clear? Similarly, now size, it may be in digit, it may be in bytes, it may be in bytes. Okay. But generally, what we are when we are doing the computer, so most likely we work on size in bit or word. So if you are very good implementer, so you want to store this 15 bit. Okay. So what you will do? 105, to store this 105, what we will do? Store 105. So simply you will give that int command and int you will define, and then one int size is 16 or 32. Okay, so that means for storing small number you are using 32 bit. 4 bit number you are using 32 bit.
That is wastage.
Okay, but suppose you have a very big number. Okay, that in the RSC you have to work on 10 to the power 2 ki power 1024 and then 2 ki power 2048. That kind of number is you are there. Then how you will store? So they have to. So you can see. So that what they do, they have to kill up that, because if computer can take 32 bit at a time. So 15, 4, 5, how many bit is required? Only 2 bit. Okay, and for 15 you require only, and then suppose you have that number. So what you will do initially 4, 5. Initially, suppose you have that 1, 1, 2, 5, 3, 9, 4, 5, 6, 9, that kind of number. Okay, so then how you will store? So for the each that number, that kind of number is there. So how you will store? What you will do? First you will need 2, 8, 5, then that, and for every digit, you will take one int, right? But it is not required. Because at a time suppose you are using 32-bit architecture, at a time computer can read 2 to the power 32 minus 1. So you have to partition that number on the basis of 32, not basis of 32, not on the base of 2. Okay. So the whole calculation you will do on that level. So you can, what you can do, you can compact your storage, and calculation you are doing on, not on bit, your calculation you are doing whole word at a time. Okay, so now you can understand what is the space complexity. It measures the amount of temporary storage used when the performing a computational task. So you have seen this, you might have done this course on algorithm and data structure, where they used to teach the big O notation and then small o notation. So what is big O notation? Suppose we write the f is order of g. So what is meaning of that? That means if you draw the graph, then both functions are growing on similar fashion. Okay. So that means f is basically g is a simpler function of f. So for example, if you take f equal to this 2n cube plus 3n square plus 4n plus 5 and gn equal to n cube. So just you will multiply something, then what you will find that f equal to order of g. So the order means that f into c into g sometimes. Okay. But it is some constant time multiplier of that function, then both will grow in the similar fashion. If you draw the graph, it will look like the same. Okay. So now the small o notation. Small o notation means that g function is growing very fast in comparison to f function. So that means the limit fn upon gn tends to infinity if n tends to 0 if n tends to infinity. So we call the gn as upper bound of this f function, and especially like fn is very less than gn. So for example, you can see that factorial n is order of n to the power n, because factorial n is nothing but 1, 2, 3, 4 up to n, but it is n into n times. So this function is growing very fast in comparison to the factorial n. So we use that kind of notation to measure the complexity of the algorithm. Okay. So you will see here like order of 1 means this is a constant. Order of that log n is doubly logarithmic function, then polylogarithmic function here, then this fractional function is 0 to 1, linear, polynomial, sub-exponential function, exponential function, and factorial function. That kind of function you will see. So now what for multiplication of algorithm, what is the complexity? Is polynomial and size. Okay. So when we are designing an algorithm, that means like encryption algorithm should be in polynomial. Okay, in size. Otherwise, what happens if we have a very heavy algorithm? So it will take long time for encryption. So then the latency issue will come. So the AES and other things is very fast. So that is why for the encryption operation, so they have to select, so that is why we are using the symmetric key encryption. Like AES is symmetric key algorithm, log cyber. So it is very fast. It is just linear. Okay. So 128 bit means 128 bit is nothing. Okay. So now I am coming to some important thing, because we are doing a lot of computation on computer. Okay. So what is meaning, like suppose you are using the 1 GHz computer. So what is meaning of that? How many operations it can perform? Speed of gigahertz. So how many operations it can perform? What is meaning of gigahertz? Or terahertz or petahertz? Yeah. So if we are using, so generally we are go market, we say no, I want high-end computer. But simply suppose we want to type this, typing and other things. Do you need high-end computer? No. So 1 gigahertz means 10 to the power 9 operation, floating point operation in a second. Okay, means approximately 2 to the power 30 operation in a second. And suppose you want to multiply the basic things 15 into 15. Okay, so how much time you should take? Suppose you have a 1 gigahertz. So 15 is basically this here. How many multiplication is required? Just I have discussed 4 bit. This is maximum 16 bit. 16 operation. Okay. So now you are using the machine, it is 1 gigahertz and it can perform 2 to the power 30 operation. So how much time it should take? Approximately 16 upon 2 to the power 30, which 2 to the power 4 upon 2 to the power 30, right? So it should take only 1 upon
26.
2 to the power 26 operation. Okay, we use the other part addition and other thing. So that means it should take less than microsecond. Okay. So that is why for the encryption and the other thing, classical computer, whatever we have, it is very efficient computer. Okay.
Sir, can we take a break?
Yes, we
3
can.
minutes?
Oh.
So you just assemble
complexity of algorithm is said to be polynomial time that I have discussed if it is a polynomial in size of input. Okay. And algorithm complexity of the form of c to the power n in every polynomial is called the exponential time complexity. So for example, like e to the power n. Okay, so this is an exponential amount. So this is an exponential time complexity. Okay, and then there is called sub-exponential function. So sub-exponential functions they have like polynomial and in between. So polynomial to super polynomial, then sub-exponential, then exponential. Okay, so this function like this one, exponential. Take simplest present, take n to the power alpha and log n to the power
minus alpha, 1 minus alpha.
okay. So an alpha line between 0 and 1. You take this alpha equal to 0. So what will come?
n to log n.
Okay. And then if take this alpha equal to 1, then this is
1. No, 0 to 0.
alpha equal to 1. Then this is
n log n.
No, into 0.
e to the power n.
n.
E to the power n.
And
So e to the power n. Okay.
Only n.
So if alpha equal to 1 means e to the power n. And alpha to the power alpha equal to
1.
1, then e to the power n. And alpha equal to 0, then log n. Okay. So that means you can see the behavior of this function. So if alpha is 0, the one is in polynomial and one is in exponential function. So it's behavior between polynomial to exponential. So what is here is decision problem is said to be class P, which can be solved with polynomial time. So all encryption algorithm, this is basically polynomial time algorithm. Okay. So now the complexity of algorithm, that is n instance, n is in integer, positive integer, is n is prime. So now answer is log n to the power 6. Because its size, it is polynomial in size of n. A decision problem is said to be class NP if S answer can be verified polynomial time. So NP, do you understand? That is non-deterministic polynomial time. Okay, so like Turing machine, then non-deterministic Turing machine. So now the here that NP problems is a difficult problem. So if S answer can be verified polynomial time. So for example, suppose we have a big number and we say that this is the factor of that number. So you can verify whether this is a factor or not in polynomial time. Okay, but you can't factor because factorization problem is a sub-exponential problem that I will come. Integer factorization problem is a sub-exponential problem. So you can't factor it. If we have a product of large two primes, then you can't factor it. For the small prime, like 15 is 3 into 5. But we are not talking about the 15. Here we have to work on the large integer arithmetic. Okay. So
NP is not polynomial.
non-deterministic polynomial time. So when you read this algorithm book, so which book you follow, I don't know, in computer science, Coreman or this Holman and Hopcroft. So they have given the model of computation that is called Turing machine. So polynomial time, polynomial time, non-deterministic automata, finite state automata, non-deterministic automata. So non-deterministic means like meaning of difference between deterministic and non-deterministic? No, what is difference? Deterministic and non-deterministic.
At a particular time, we can
See, for the deterministic algorithm,
we can determine the polynomial.
For not deterministic means no solution as per.
no. That is, you can say one of the example. I am giving you the very simple example. Suppose you want to calculate pi,
Value of pi.
value of pi.
20%.
We have a deterministic algorithm.
22%.
Can you find the solution? आप करते जाइए, जब तक आप स्टॉप नहीं कीजिएगा ना लूप को, यू हैव टू स्टॉप द लूप समवेयर. ठीक है, तो नॉन डिटर्मिनिस्टिक मशीन डिटर्मिनिस्टिक मशीन है, नॉन डिटर्मिनिस्टिक मशीन. डिटर्मिनिस्टिक मशीन में आप क्या है कि फिक्स इनपुट के लिए हमेशा फॉर द सेम इनपुट यू विल गेट द सेम आउटपुट. क्लियर? बट व्हेन वी हैव अ नॉन डिटर्मिनिस्टिक मशीन एंड द नॉन, क्योंकि इफ वी कांट सॉल्व द प्रॉब्लम बाय डिटर्मिनिस्टिक मशीन, तो द ईच स्टेप that machine has to take the decision. Okay, each step machine has to take the decision what like where I should go. They have a multiple option and where I should go. Okay, and then machine will take the decision. Then again that next step, what will happen? Again we have a multiple option, and then machine has to take the own decision. So we don't have any deterministic routine there. Okay, so that is called the non-deterministic. So I think you should have some read this book, algorithm book. This is very important. Okay. So now we have a certain kind of decision problems that is called when the two problems are equivalent. So we are saying suppose two decisional problem and then L1 have decisional problems. So when they will call the equivalent problems. So that means L1 has to be polynomially reduced to L2. So first polynomially reduced problem and then equivalent problem. So two things. So L1 is said to be polynomially reduced to L2. That means we write the L1 is less than equal to P L2 if there exists the algorithm that solve L1 using only the polynomial calls to an algorithm that solve L2. So that means as a subroutine. So if we can, what is meaning of that is, suppose if we can solve this algorithm L2, then you can call L2 to solve L1 as well. Okay, as a polynomiality. So and then similarly we have a concept like so if L1 is polynomially reduced to L2 and L2 is polynomially reduced to L1, then we call that the polynomial equivalent, that's the equivalent problem. So some like integer factorization problem, and that is called the quadratic residue problem. I will tell subsequent slide. Like so this is a relation. If we can solve the integer factorization problem, then we can also solve the quadratic residue problem. So now we are coming to the NP problem, NP complete problem. So NP we have discussed. If S answer can verify in the polynomial term, then it is called the NP problem. Okay. Now a decision problem is said to be NP complete. So when we see that NP complete problem, if first this is the NP problem, and the second, if any other NP problem is there in the set, then it should be polynomially reduced to L problem. So the example of that, like subset sum problem. So are you aware about the subset sum problem?
Yes.
Knapsack crypto system. So subset sum problem basically is a NP complete problem. Okay. So what is this subset sum problem? Is it given a set of positive integer and positive, given a set of integers, this is a a1 to an and a positive integer n, determine whether or not there is a subset of ai that sum to s. So this is a subset sum problem. So this is a NP problem. Okay. So now we are coming to NP hard problem. So this is the hardest problem in the NP set. Okay. So the example of NP complete problem is a computational version of NP complete problem. That is a NP hard problem. So, if we have that kind of set in subset sum problem, then find out that set. Computationally determine that set. Okay. So, this is the diagram that how we are related to this different problem. Okay. So, which one is NP, the set, how we represent this NP problem, then NP complete problem, then NP hard problem, then this here, bounded quantum polynomial time algorithm. So, some relation is there in decision problems. Okay. So, just we have finished this part. Very basic about the complexity. So, complexity is very big topic. Because this we are going to use further. So, for understanding this public key cryptography, we should have a good knowledge of Euclidean algorithms like number theory, Euclidean algorithms, modular arithmetic, arithmetic function, their properties, solution of linear quadratic congruence, Chinese-Mendel theorem, primitive probability testing, and integer factorization problem. These are the important topics in number theory that we use in public key cryptography. Even in the others also, many other protocols also we use this concept. Then in the finite field, algebra and finite field is very important in this area of public key cryptography. That is irreducible and commutative polynomial, method for testing them, function and their basis, normal basis, polynomial time basis, arithmetic over finite field, factorization problem, and many commutative problems. So that's this we have just stated like problem. Okay. So now we are coming to the hard problem and one-way function. Okay. So we are saying that some problems is hard problem. Hard problems, hard means the computational infeasible. Okay. So that the complexity is 2 to the power 256 kind of thing. So current scenario. So we are writing it is in current scenario. So it will change. It may change if we have that kind of computational infrastructure. So what is here is means a complexity is 2 to the power 56. Why it is hard? Why it is hard? Why it is hard? So why it is hard currently? Why we are saying it is hard? We don't have any computational infrastructure to solve that kind of problem. If complexity is 2 to the power 56, and why we don't have computational infrastructure? You can see, you know, you have a PC and everything. So, suppose you have this 1 gigahertz PC. So that is approximately 2 to the power 30 operations we can solve floating point operation. Okay. So now, suppose you have so now currently we are having all the PC, either is quad core or octa core. Okay. You multiply that factor, octa core multiply by 8 times. So that is will be 3. Okay. But your complexity is, so how many that kind of system is required? Okay, so this is just an example. So now, suppose you have a machine with terahertz, that means 10 to the power 12, approximately 2 to the power 40 operations. Okay, you run this machine whole day. Okay, so whole day means
24 hours.
how many seconds are there? 86,400. 16 to 16 to 24. Okay. So this is approximately 2 to the power 16.5 or something. Right? Then you run it for 365 days. Approximately 2 to the power 8.5. Okay. So So now you multiply tera has machine means 2 to the power 40 plus 16.5 plus 8.5. So how much it is coming? It is approximately 2 to the power 65.
75.
And then your complexity is this level. So even teraflop machine, how many that PC you are required and how many times you will run that PC. You run that thousands of years, still you will not be able to solve that problem. Okay. So this is why this is hard. If you are taking the complexity to 256, in the current scenario it is hard. Suppose we have we don't know in the future what kind of computational facility we will have. Okay. So now the AES, that's here we have mentioned the ECC. So elliptic curve cryptography, if you use the key size, if you use the field size, 100 to 500 tolerance, so its complexity is approximately 2 to the power 256. Okay. Now we are coming to the trapdoor one-way function. So trapdoor one-way function is easy to compute but hard to involve. So if you have two large and this numbers, you want to multiply them. So you know the multiplication is a polynomial time algorithm. So you can compute easily. But two numbers is a big number and you want to factorize. So factorization problem is a difficult problem. It's some exponential complexity. So it is hard to invert. Okay. So the most important concept we use in the public key cryptography is one-way trapdoor function. So one-way trapdoor function so trapdoor function, if you know something about that, then you can invert. Okay. If you know some information. So like, if you know one factor, then you can find the other factor also. So if you know some information, then you can invert. Otherwise you can't invert. Okay. So now, for example, suppose like this n equal to pk, and this is basically RSA kind of system. So I'm going to discuss. So in RSA, what we do, we simply do the x to the power e, and you have to find out the p inverse modulo this phi n. Phi n is Euler function. So you know the phi n. Let's say Euler-Torsion function, and so if you know the factor, then you can compute phi n. Otherwise, you cannot compute phi n. So if you know the factor, then you can compute phi n, then you can find out the inverse. Otherwise, so then you can compute the you can invert this function. So what are the mathematical problems which we use to design a public key cryptography? That is integer factorization problem, just I discussed, subset sum problem, quadratic residue problems, discrete log problem in finite field. These are the important mathematical concepts, DLP literature over finite field. Then different version of that, computational Diffie-Hellman problem, decision Diffie-Hellman problems, conjugative search problem. These are all mathematical problems, and all these mathematical problems is computationally intensive. So, so to break the system, you have to solve these kind of problems. Discrete log problem with conjugative search problem, certain problems like then solving system of that multivariate polynomial equations, the general decoding problems, lattice switch problems, has okay, and then the computational supersimilar isogeny problems. These are the very important mathematical problems that we use to design a public key cryptography. So now I am coming to the present situation. Okay, so what is the present situation? Widely known encryption scheme RSA, eligible, digital signature RSA, ECDSA, key exchange protocol like RSA. RSA is not key exchange protocol, by mistake it is written. Diffie-Hellman key exchange protocol, EC Diffie-Hellman key exchange protocol. Okay, widely known algorithm, AES you know, SHA-2, SHA-3 you know. So these are the currently we are using, widely known systems. Okay. Yeah. So just for the completion, you know what is RSA? RSA everyone knows? Okay, shall I Is it required? I can skip. Okay. So what is RSA? So here we have mentioned the integer factorization. If you can find the P and Q, then what is then the find message can be that message can be decrypted without knowledge of key. So how we will compute it? Because if you know the P and Q, so here yes you will go back. If you know the P and Q, so what is Phi n is? Phi n is nothing but P minus 1 into Q minus 1. So if you know the P and Q, then we can compute Phi n. And then this, once you know the Phi n, then what here what is public key? Public key is basically in case of RSA, this is E, and then the decryption key is D. So if you know this, then we can compute the Phi n and we can find out the inverse. But if you don't know the product, then we cannot find out the product. The whole problem rely on this. Okay, so this is the example. I am going to discuss this RSA. Now I am coming to another computer system based on the discrete log problem. So discrete log problem, you know what is discrete log problem. So group and other things, I think everyone will be knowing. G is a group, cyclic group. Okay. So sometimes we also write ZP also. Okay. Cyclic group, and alpha is generator of that group. So what is meaning of generator? So generator, it can generate whole, how many elements in ZP star? Just to take 1 to P minus 1. And alpha is generator. Generator means it can generate all the elements. Group with respect to multiplication, so G equal to ZP star with respect to multiplication. Okay. It can generate all the elements. So we can also write alpha is the generator of this, G equal to alpha. Now given alpha to the power beta, and we have to find out x. P is very big. So it means the size of P, size of ZP star, cardinality of ZP star is suppose 2 to the power 204. Okay. So then we have to find the value of x. So x is small, then it is easy to find. But if this group is very small, then you can do manual calculation. But if group is very, very large, then again this is some exponential algorithm to solve this problem. Okay. So just you take the small example here. Okay, so we have taken the size of this piece 19. Okay. Now suppose you want to find out the this 2 to the power x mod 19 equal to 50. So now you find out the value of x. So you can do the manual calculation, just 1, 2, 3, 4, 5, and when it is matching, yeah, at 11 it is matching. Okay, so that means x value is 11. So this is the simple example of discrete log problem. So here, so now this is the first key exchange protocol based on the discrete log problem. So suppose you want to exchange the key, then what we will do? We will have that group with alpha as a generator. A will select one secret key x, and he will compute alpha to the power x and send to B. But you know the discrete log problem is hard. So from the alpha to the power x, we cannot compute x. Given alpha to the power x, we cannot compute x because the discrete log problem is hard. Okay, and similarly, like that B selects by, and he will compute alpha to the power by. Okay, and he will send it to A. So now x is secret key of x. So he will get A will get the alpha to the power. A will get the alpha to the power by from B, and he will simply he has to take the power x. So he will get the alpha to the power x by. and B has a secret key by, and B will get the alpha to the power x. So he has to simply raise the power to get the alpha to the power xy. So finally both are getting the same key alpha to the power xy mod p. Since the discrete log problem is hard, so he cannot compute given alpha to the power x and given alpha to the power y, we cannot compute x or y. Or given alpha to the power x and alpha to the power y, we cannot compute alpha to the power xy. Okay, so this is how the discrete log problem is. Example of crypto system, I think we can skip or okay. Here, irrigable crypto system example. So now the current protocol is another, that's elliptic curve cryptography. Okay. So as you have seen here, in particular irrigable crypto system, what is the irrigable crypto system? Irrigable crypto system, what you need? Here you need one group. Okay. And then what you need? Here some you need one generator, okay, of the group. After that, we use the discrete log problem to design this protocol. Okay. Irrigable system, you know this. You know it's required to explain.
It is similar to Diffie-Hellman.
Yeah, it's similar. Concept is similar to Diffie-Hellman. Okay. So because the discrete log problem is hard, so whatever here we are using for the encryption technique, we are using the concept of discrete log only. So we have to have some structure. So here in the irrigable case, what we have a group and then generator, and then we are using the operation on this group only. Okay. So now can we have some alternative group? Can we have an alternative group? And why we can't use elliptical? Why we can't use only the irrigable? Can we have an alternative group or not? So in case of this irrigable crypto system, it is based on discrete log problem on group. So this is a sub-exponential problem. If you want to solve the discrete log problem, so it is a sub-exponential. But to increase the security, we will discuss the key size later. To increase the security, the researcher thought that we should have some alternative structure of groups so that our discrete log problem is harder than the current current problems in natural group. So this is generally we are using the natural group. Okay. So in the elliptical is also the elliptic curve is a curve. It looks like this way. Okay. Here. And set of points on elliptic curve. Set of points on elliptic curve forms a group structure with respect to the point addition. So then the Koblage and other Victor Miller realized that because it forms a group structure, so we can also use in cryptography. Okay, so here, so this is the most generalized form of elliptic curve. Weierstrass equation, we call this Weierstrass equation, and then set of points on this Weierstrass equation forms a elliptic curve. Okay, so now since we want to implement the things, so if we have a finite set, because like in the group we have taken the P and we have to take the size of P is very large. For the implementation of elliptic curve, we have to, how we will implement these things? Because we have to rely it finally in implementation. So then later on rely, if we use it over a finite field, then its structure preserved and it is also forms a group. So what they have done, like they have said that elliptic curve, since the if we take finite field, so initially they have taken the any field means the constant R belongs to some field. So either constant can be like this is the curve. Okay. So we are saying curve defined over the finite fields means the all the constant are the element of field. So constant can be an element from real so real number, set of real number is also field, set of complex number is also field. So constant can be taken from the any field. But for the elliptic curve, for the cryptographic purpose, we have to use the finite field. So finite field, for example, ZP is also finite field. So finite field, you know the what is definition of field? What is definition of the group? So group means satisfy the certain properties. But what is field? So in the field, in the group we have a single operation. In the field we have a two operation. Okay, so with addition and multiplication. So in the case of field, like it's perform its group with respect to addition, and non-zero elements also form a group with respect to multiplication. So it is wider structure. Okay, because it has a two operation here. So now the like ZP is also finite field. So ZP forms a group. So the constant can be taken from finite field also. So for the cryptographic purpose, we have to use the elliptical over the finite field. Okay. So we have to take the non-singular curve, and then so there is this property when this curve will be non-singular, and what kind of field we should use. So what that the set of points form a group, set of points on the elliptical over a finite field forms a group, and then with respect to the point addition. So how we will do the point addition? Suppose we have a P plus, we want to P is another point, Q is another point, and we want to add both these points. So there is a formula that can be used to derive P plus Q. Okay. So in a ZP, like it is multiplication with respect to mod P. Similarly, this is a group with respect to addition, and addition is formula is given by this x3 and P plus Q equal to x3 and y3, and x3 and y3 is given by this formula. Okay. So suppose graphically, suppose we want to multiply the P and Q. Okay, so that you have seen that this is a cubic equation. Okay, elliptical equation is a cubic equation. Y square plus even x square plus this equal to x cube plus 3x square. So this is a cubic equation. Okay, x in x here. So suppose we want to add the P and Q, and we want so we draw the line from P and Q. So since the equation is cubic, so definitely it will intersect at another point of the curve. So it is intersecting R, and then we take the reflection. So P plus Q is nothing but this point. So again the P plus Q is also element of elliptic curve. So that is how, so all the property of group with respect to the point addition you can see. So this is the point P, and you want to add that point again, P plus P. So you draw the line, then it will intersect at that point, because P plus P, and then take the reflection. Okay, and then suppose you want to find out the identity. So identity means P plus 0 equal to P. So suppose P is the point P. Okay, and identity we consider the point at infinity. So now you want to add this point and this point. So it will intersect as third point, and then take reflection as P. So that means P plus 0 is nothing but P. Okay. Similarly, like inverse. So you want to find out the inverse of P. Okay. So just you have to take the reflection of that point. So P, like use P, and this will be minus P, because you add this point, then it will intersect the third point at infinity. So that means like addition, your identity, your inverse, all things exist. So that is how this elliptic curve forms a group. So now, like since we have to work in the discrete set, so we are taking the finite field. So we have a clear cut that formula to determine the number of points on curve. Like ZP, you can clearly know that how many points are there. How many, similarly, the formula is there, you can determine the number of points. So that means all the theory is available, that it is a forms a group, we can determine a number of points. So we can use this for designing a cryptography. So based on that, we have a many public key crypto system. Okay. So normally, like for implementation purpose, either we use the finite field, binary finite field, that is this set contains 0 or 1, or we use the prime finite field, prime to the binary to the power higher extension, or prime to the power lower extension. So here for the certain for the binary, we can transform the original equation to the simpler equation. So these are the simpler equation in case, suppose the field we are taking characteristic 2, we are taking characteristic 3, and we are taking higher characteristic. So these are the simpler version of the elliptic curve. Okay. So how will we realize, suppose how you will realize if you are the discrete set. So these are the discrete set. So discrete set basically point in the two-dimensional space, discrete point. And this is the P and Q. Okay. And you want to add these 2 points, then it will definitely will have a third point and take the reflection, this reflect image. So this will be P and Q. So these are the discrete set. So for the practical realization, it will look like that, this graph. Okay. So in this case also, because it forms a group, so in this case also we can define an elliptic curve discrete log problem. Because without mathematical problem, we can't design a system. And the complexity of discrete log problem is exponential. So suppose n is the size of field, then complexity of solving elliptic discrete log problem is 2 to the power n by 2. So this is an exponential problem. Okay. So whole for the encryption and decryption process, if you want to design elliptic curve, this is easy. We can do the encryption, decryption, or for the design any schemes, all the operations are polynomial. But if you want to break the ECC based system, then its complexity is exponential. Okay, so these are the some name of the system which schemes based on the elliptic curve. I am not going to discuss the system. Okay. So what is the here advantage? Like in RSA, suppose we are working on size of group is 1024, then in case of elliptic curve we have to work on field size only 160 bit. Okay. In the case of so if you use the formula to determine the complexity, the final complexity for the elliptic curve, it is coming the 160. If you are using the symmetric key cryptography, then it's equivalent to 80 bit security. But we are using the AES 128. For that, we have to use RSA, and the RSA or eligible, where the size of eligible, where the size of group you have to use 3072, means the size, which is the group number of elements in the group should be 2 to the power 3072. That big group you have to use. But in case of elliptical cryptography, we have to take the finite field of size 2 to the power 56, means the field number of elements in the field is approximately 2 to the power 256. So that is how, like, because we have to work on a smaller size in case of elliptic curve, so we can implement the complexity of this encryption and description algorithm, complexity of this algorithm in comparison to the RSA, it's not that complex. Okay, okay. So encryption and decryption operation we can perform in polynomial time, but with the smaller size, we can get the same level of security. same level of security. Okay, so that is why people have used elliptical cryptography because initially the very hard mathematical concepts are involved. So people are finding the difficulty to implement these things. Now it is very popular. So in place of RSA or invariable, people are using the elliptic curve also. Okay, so this is how the complexity graph. Okay, so advantages, because shorter key length translates to faster implementation, less power consumption, less silicon area. So we can implement in the small microprocessor or something for different devices. Now I am coming to the impact of quantum. So what will happen when we have a quantum computer? Okay, so as you know, if key size is n bit, then traditional computer requires 2 to the power n number of operations to do the for breaking this. Okay, if you use the exhaustive charge, 2 to the power n operation, but quantum computer can perform this operation in 2 to the power n by 2 using global search algorithm. Okay, then other things like we have other algorithms like Siemens algorithms, and then quantum collision search algorithm. But some additional things also play the important role while implementation, like how many quantum logic gates are required. Okay, so next thing is like currently what we are using, RSA problem, Diffie element problem. Okay, and all the this RSA and Diffie element problem, if you use the natural group, then sub-exponential, and if you use the elliptic curve group, then exponential problem. So this example here. So if you are using RSA and this Diffie element key exchange equivalent, so we have the general number field series algorithm whose complexity is sub-exponential. And in case of elliptical discrete block problem, we have a polar row algorithm to solve the ECBLP whose complexity is exponential. Okay, so that key size comparison I have discussed here. So like to this, suppose we are using elliptical distance signature algorithm, where the field size is 224, so it's providing complexity to the power 112. Okay. In case of AES, 128 bit from the classical computer is provide the security of level to the power 128. So in the Peter-Shor, now this is the important algorithm. Peter-Shor said the integer factorization problem can be solved in polynomial time, the size of n. So what will happen? What is the current algorithm? Current algorithm is sub-exponential algorithm, and this is the exponential algorithm. But they are saying if we have a sufficient large quantum computer, means large million of qubits we have, then we can use that computer to solve the integer factorization problem, discrete log problem, elliptical discrete log problem. So means this security relies on integer factorization problem, or security relies on discrete log problem, can solve in polynomial time. So when we can solve in the polynomial time, that means we can solve it very quickly. So we can break these systems. Then what kind of problem we should use now? Okay. So that slide we can skip. QDA means like when we will have that kind of quantum computer, then we will call the QDA. Okay. So what we have to do? What we will have? What is the impact? So all these problems like quantum computer, integer factorization problem, discrete log problem, discrete problem in general group, RSA, everything will break. Global search algorithm can be this avoided by doubling the key size. So now like suppose AES 128 bit we are using. So from the global search algorithm is 2 to the power 64. So we use that, we can double the size. Okay. So in symmetric key cryptography, just after little bit twisting, you can survive with the existing algorithms, but by doubling the size and twisting the algorithm. But PKC, you have to change the mathematical hard problem. So now we are coming to post-quantum cryptography. Means once we have that kind of computer, then what kind of public key crypto system we will use. Okay, so we have a certain mathematical problem, that is lattice-based crypto system, code-based crypto system, multivariate-based system, isogeny-based system, hash-based system, which will be secure in quantum era. So just now, because since last decade, a lot of work has been done in quantum computer. So in the last decade, lot of work is being done by in post-quantum direction as well. So NIST, National Institute of Standard Technology of USA, they have announced the competition for post-quantum cryptography. Like they have asked researchers to submit the algorithm which will be secure against quantum attack. So so they have submitted. Then last date was 2017 December. And, so then after the submission, they have submitted the status report. 82 crypto algorithms submitted. A 69 candidate algorithm which satisfy the minimum criteria. And first, after that, in the Jan 2019, second round competition they have derived, where they have submitted 19 algorithms for the public key encryption and key exchange mechanism, and 09 algorithm for digital signature. And the second round status report published in 2020. Then July 2020, third round announced date, where they have a 07 candidate, that is 04 for encryption and key exchange mechanism, and 004 signature scheme they published, and 8 alternative algorithms have been published. So these are the algorithms. So public, and these are the alternative candidates. So some candidates are based on like code based, some is NTRO is based on lattice. Okay, Rainbow is based on multivariate crypto system. Here, and then Spinach is based on hash based concept, and then Psych is based on isogeny based. So here we have discussed like, so now the post quantum cryptography, either they have based on lattice, or based on code, based on multivariate, based on isogeny, or based on hash concept. So we have a lattice based hard problem. So now I am going to come to the slowly on the lattice based hard problem. Okay. And okay. So additional, they have also, because the signature scheme, because of the less signature scheme, they have also announced the additional card to submit the more signature scheme. So initially we have like received the 40 candidates for signature, and in the second round also, that round 2 also we have received the 14 candidates. So first initially we have received the 14, then only some scheme and that's broken, and then got broken, and then finally like they have the 14 in the second round, they have a 14 schemes for the signature schemes. Now they have defined the security level. Security level means scheme should provide the security level equivalent to AES 128. Means that whatever scheme they have submitted, if they are providing the security level 128 bit, or they are providing a security level 190 bit, or they are providing a security level of 256, and are in post quantum era. Okay. So now we are coming to lattice. So what is lattice? Most of the you people have read the vector space. Okay. And then dimension of vector space, finite dimensional vector space. So lattice is also kind of one kind of vector space, but here the difference is, you can see here, in the vector space is defined over the field, but the lattice is defined over the ring. So all the if B1, B2 is the B1 to Bn is basis of this lattice, then it is a linear basis, then it is a linear combination of n vectors and the coefficient are from the Z. So since it's coefficient from the Z, so that is why it looks like this. Suppose this is the V1, this is the V2, this is V3, then you take the linear combination. So this is all the sets you can see here of this lattice. So linear combination of vector, a linear combination then over the ring. So here we have a lattice based problem. So what is the shorter vector problem? So suppose you have a vector n vectors, and if you want to find out the shortest vector in that. So shorter vector means norms of vector should be minimal among the all vector. So this is the hard problem. And then closest vector problem. So closest vector problem means if we have a two vector, then if we have a given a vector and then find out the other vector which is closest to that vector. Okay. So we have a certain mathematical problem like this kilo problem in the group. We have a certain problem in lattice like shorter vector problem, closest vector problems that can be used to design a crypto system. So lattice based is the most popular crypto system nowadays. Okay, and then like the shorter vector problem and closest vector problem is finally it's a reduction. We can reduce this problem to the learning with error problem. So it's most of the crypto schemes are based on the this learning with error or short integer solution. So what do you mean by learning with error? Suppose you have this equation. So A1 is vector, S is vector, okay, and then we are taking the inner product of that. And we have a vector V1 to Vn. So you can see that it will convert it in the set of equation. But suppose we introduce some error here and introduce some error. Okay, then how to find out the solution of this? We don't know error, even E2 to En. So we don't know this error. So then how to find out this solution? So this is the concept of learning. This is it, learning with error. So now what here is, you see, so suppose what we are getting here is A1 equal to this, A1 equal to inner product of S1 A1 here, this B1 equal to this. So here we have a matrix and then B is this second part. So B is nothing but S to the power A and we have introduced the error. So if you remove the error, then we can find out the solution. Otherwise, if you induce the error, then we have to use the remove this technique for removing this error. So on the other way, basically, suppose like we have to distinguish vector A and vector B from the uniformly random A and B. So this is equivalent to that. So once we have introduced the error, then it is we cannot solve the solution. Otherwise, we can solve this system of equation. So this is the based on the lattice. So this is the first crypto system, LWS public key crypto designed by this author, Audit Rigby, in 2005. Okay, so how it works? Like we take we take random vector S. Okay, so vector S over Q of n of dimension n. So basically, element R belongs to the ZQ, and then this dimension of vector is n. So we take the vector S and we take the matrix A. Okay, random matrix A, and then we have to use the error vector now. So error vector, what is the error vector? So error we are taking, just you can see here this previously in the slide, error. So E1 belongs to ZQ, U2 belongs to ZQ. So suppose this is the length n, so this will be a vector from ZQ n. Okay, so this is the vector from ZQ n. So now we have this. Now you can see we can compute the this matrix into the vector plus E. So we can compute B from this. Okay. So what is the public key here? Is public key is A and B, and secret key is S. So suppose you want to encrypt some message 0 or 1 bit. So this is we are talking just 1 bit encryption. Okay. So what we will do? Here we select the another random S, and then we compute S dash A and inner product S dash and vector B. So B is public, A is public. Okay, this is public key. So we can compute these S dash as well as S dash. We can compute this A and V. For decryption, what we have to do? C is nothing but this. So now this ciphertext is A and this is C. Okay. So now what will be what we have to compute? We have to compute S dash C minus A dot S. C minus A dot S. So A is not. So now C is S dash A and S is here, and what is here is S dash B is B. Okay. So computes C minus A dash S, and you can see here what is this, and you find out then we check whether the S dash minus 0 is less than X dash minus 2 or not. So if it is less than 0, if it is less than this, X dash minus 2, S dash minus 0 is less than this, then we have encrypted 0. Otherwise, if it is greater than under model 2, if it is not less than, if it is greater than, then that means we have encrypted 1. Okay, so this is the first scheme based on the lattice. After that, we have many such schemes based on the lattice. Here since we have in the system of equation, what we have done, we have introduced this error. So what is the this? Suppose we want to find out the this error. What we have added this error? How do you find out? So what is the complexity? So since you can see here, because each vector is from the Q. Okay, so each vector of from Q. The selection of Q means, and then we are the n vectors. So that is a Q to the power n. Okay, so that is why this complexity is exponential. Okay, so this lattice-based problem is a computational hard problem, and this is problem is NP hard, which means that there is no non-polynomial time algorithm to solve this lattice problem. Okay, so we have some we have many algorithms to solve the lattice problem, but all are exponential. So these are the algorithms that can be used to solve the lattice problem, but they are all exponential problem. Okay, and complexity of this finally, suppose the dimension of this lattice is D, then complexity of this is the best known algorithm is complexity of this is exponential. This is 2 to the power order of D root or 2 to the power order of square root of D log D. Okay, so this is the best known algorithm to solve, and this is the exponential algorithm. So based on this lattice concept, because currently we don't have any quantum algorithm which can use to solve this in polynomial terms. So that system can be used. This system can be used for designing public key cryptography, and that will resist the quantum attack. Okay. So some this NIST selected this parameter. Another concept second concept is solving system of multivariate polynomial over a finite field. So system of equation. So system of equation over finite field. So suppose we have a system P1x, P2x, system of equation. These are the systems. And P1x equal to 0, P2x equal to 0, and where each Pi is quadratic in X. Then all coefficient and variable are in finite field FQ. Okay, with the Q element. Now we want to find out the solution of that equation. So this is the again NP-hard problem. So based on that, and based on that, we have a crypto system, and as of now we have no quantum algorithm that can be used to solve this problem. Okay, so in fact this is a doubly exponential algorithm, but when we design the algorithm, from the one angle we have to see the we see the p size, what kind of we see that we determine the this security of this algorithm based on the complexity. However, sometimes designing algorithm, people are designing the algorithm, they also leave some protocol weakness while they are designing. So in addition of that, our mathematical problem, we have to see the protocol design as well. There should be no protocol weakness. So even this schemes, we have taken the mathematical hard, very best this computational hard problem. Still, initially the scheme proposed by Rainbow scheme based on this multivariate, but we have got the attack on this algorithm because of the protocol weakness. Okay, so these are the complexity of what are the algorithms that can be used to solve the multivariate system. So global basis algorithm are technique, and the complexities you can see is W exponential. Then Bidman Excel techniques are there. You can see the complexity of algorithm again W exponential algorithm. So that multivariate crypto system based on this, and then these are the parameter size that we have to use. Okay, field size, and then the size of field, size of equation, how many equations we should use, how many beginner variables are required, these are all things they have to use. Okay. So that schemes, that multivariate based scheme that I discussed, that one. This one, Rainbow. So Rainbow is based on this multivariate crypto system, but even that this is a hard problem, it's based on the hard problem, NP hard problem, but still we have got some attack because of the protocol weakness. So from the mathematical hard problem, and another is from the protocol weakness. So we should not have, while we are designing the scheme, we should not have any protocol weakness as well. So the RSA and other systems, they are designed in very well manner. They are not having any kind of protocol weakness. But sometimes the scheme, because they are these schemes submitted recently, people are trying to find out the weakness from the other angle as well as, in addition to the mathematical hard problem, because mathematical hard problem is difficult to solve, and we don't have any algorithm which can be solved in a polynomial time. So people are trying to find out the different way to attack. So when we design the scheme, it comes in the public domain, then researchers try to break it from the certain angles. So sometimes what happens, the protocol weakness is also there. So that is why people leave it in the open domain. If someone try to find out the weakness, then they publish, this kind of weakness is there. Even the mathematical hard problem, that computational hard problem is good, but still this scheme is not good. So even so that is why the NIST, AES came, that is how the AES came. Because initially lot of algorithm, NIST announced a competition for this symmetric key encryption, and a lot of algorithm they have submitted in 1998 or something. Then later on, they realized that the many algorithms which have been submitted in this competition is not secure as per claimed by the designer. So they have been rejected, and then finally the AES came because it was secure. There is no, even now we don't have any non-attack which can reduce the complexity drastically. So similarly in the public key cryptography, now because they have started the competition and they have submitted the many algorithms in the domain. So somehow some of them got rejected immediately, and some of them are still surviving. So if there is no other protocol weakness, then we can say that, and there is no quantum algorithm to solve evaluation. So now we are coming to the code-based, code-based things. Okay, so directly first I will come to this figure. So code-based techniques is, we are using code-based technique for error correcting. Okay. So what do, in the first figure I told one thing, we are using error correcting technique, right? So what we are doing here is, how do we error correct? Like suppose, like we want to send a message, okay? We have to encode the message, and after that we send it to a noisy channel. What will happen? Like because of the noisy channel, some this bits will be corrupted. Okay, and then we have to remove that error to recover the message. So this is the general principle of coding theory. And the coding theory also, like apart from this cryptography, that coding theory we have been using since long. The reason is that because in the all the noisy channel, the like finally what happens, we don't get the original message. So can we use this coding technique for encryption also? The same concept of coding we have used for encryption. So earlier what we are doing, the error is coming because of noisy channel. But here what we do, we introduce the error by ourselves. Okay. So here, like we see, so here we use the encoding and then we have a noisy channel, right? So we will get the C. So we encoded message and then C, and then we are sending it to C into noisy channel. So error will introduce, finally what we will get? C plus C. But whether, how we will get the C plus from C plus E to C? This is the problem here. So we have a certain like problem based on this concept. So suppose like we have a message mean, in the coding theory we use generating matrix, parity check matrix, this kind of concept we use. So suppose we are sending the message, okay, and then G is the generating matrix, okay, to convert into the code form, and then we have an error E. Now for the removing the error, we use the parity check we use the second technique, removing the error. Now H is the parity check matrix, okay. So the concept is that if you multiply by H, so what will happen? G and H will cancel out here, and we will get the E into ST. Okay, this one here. Now this is called syndrome. Okay, this part. So as it's called syndrome, so finally the problem is to call it. So okay, so, and formally this problem is called as computational syndrome decoding problem. Now we have to find out the error from this. Okay, so given a S and H, and we have to determine the syndrome. So this is called the syndrome. So this is the computational hard problem. Okay. So also known as the computational syndrome decoding problem. And in fact, these problems, the gender decoding problem and computational syndrome decoding problem, they are the anti-complete problems. And based on this concept, the McLeish and this designed the first code-based crypto system. Okay, so now like for every problem we have some solution. So we have many algorithms that is for find out the solving this computational syndrome decoding problem. So information set decoding is the concept to find out the error. But almost all these information set decoding algorithms are exponential in nature, and all the computational hard problems. Okay. To find out the error, we use this algorithm, and that is how the public key crypto system based on the coding have been public key crypto system based on the coding have been designed. So these are the all information set debugging also. Almost all problems are exponential, and you can see this is the complexity of this algorithm. It's very complex notation. So complexity of the syndrome decoding algorithms is this. Okay. So what observation we have that complexity of gender decoding problem is exponential. So security of these crypto systems rely on the difficulty of solving computational problem or equivalent problem. Okay. So in addition of that, like as I said, because they that crypto system when we design they leave some other protocol weakness as well as so some structural attack is there for many crypto systems which were submitted earlier and different techniques. In addition of that, like if we are using this lattice-based crypto system or code-based crypto system, the size of key is very large. Okay. So size of key is large, so that is why like during the implementation in hardware and other things, other devices, we are finding the difficulty. So people are now you can see like for the certificate and the digital signature now we have a token presently. In token what algorithm they are using RSA and other things. Okay, because of the size is small. But here the size of public key is very large. So I will tell that what is the size in the next. So to to cater the size, people are trying to give the new proposal on code base or lattice base, so with the smaller key size, smaller field size and other things. But still, implementation it has a lot of implementation difficulty. So, near future they are trying to replace the token by they are trying to replace this token which are currently using the traditional classical algorithm. They will replace some post quantum algorithm, but it may be initially the size is big, but later on they will try to find out some other solution to make it compact size. So this Macaulay published the first system in 1978, and just we will give gist of this system here. Like we have to choose the finite field, then we should know the which code we are using to design a system. So now lot of in the coding theory, lot of work has been done. We have a Reed-Solomon code, we have a Reed-Muller code, we have a Hamming code, we have a lot of codes are there. So what kind of code we should choose to design the system? So that we can do the encryption description fast to reduce the key size. That is still challenging. Still challenging. So in coding, and the second thing, how much then how much error correcting code, whatever code we are using, then there will be the capacity at how much error we can correct. Okay, how much error we can detect, how much error we can correct. So we write the coding in NKD format. So that means another dimension NKC. So if you are using this here, suppose this 2 to the power n. Okay, so 2 to the power n. So that is why we have so generally we represent NKD format in the code. So n and then k is the dimension of code, n is the field size, f to the power n, k is the dimension of code, and then NKD. So D is basically you can how much error you can correct and how much error you can detect. So T is the error correcting capability, and D is basically how much error you can correct. So Hamming distance, D is also called Hamming distance. So that way like some important things, some that notation is written, and then suppose we are using the, in mechanized system they have used this one, Gopa codes, mechanized. So Gopa codes, and this is GZ is Gopa polynomial. So first we have to know the which code we are using. So suppose we are using the Gopa code, then we should have a generating matrix of that Gopa code, and size of this matrix is K cross N, is standard things in the coding theory. Okay, and then suppose like you want to encrypt some message, then you should have a public key and private key. So we have to choose matrix S and matrix P carefully, and then here the one matrix is called one matrix G star. Is G star is nothing but G, S, G and P. So you can see here, this is the public key. So what is the size? Size of public key is a whole matrix, and then you have to see that where you, over what you have defined the matrix, what is the field size and everything. So this is the size of public key is a whole matrix. Okay, so that is why the size of public key is high in this code-based cryptography. Okay, and then what is SGP is a secret. So you can see the triplet is secret. Yes, 3 matrix is secret key size. That is how you can see the size of this public key and private key. Okay, so to encrypt the message, what we will do, simply M into G star plus E. So encryption technique is easy. Just we have to do the matrix multiplication and then matrix addition. Okay. And for the decryption, what we have to do, the secret key is SGP. Secret key is SGP. So first we will do the by P inverse. So we will get the MGP inverse plus EP inverse. And then P inverse will be cancelled out, because this is P inverse will be cancelled out, this one. So what we will have it here, MS G plus EP minus 1. Now we have to use the, so we have to use the code which we have an efficient decoding step. Okay, so this is the important concept in the coding theory. We have to use the efficient decoding algorithm. So we have to choose the code carefully. So decoding, so now what we will do, we will use the decoding algorithm to find out MS. And then finally we do the M inverse to recall the message. So intentionally we have introduced the error here. Okay, now you can see that simply the complexity. So what is the size of this vector? And then, so if you know these things, then if you know the error, in advance, then you can compute, you can try to break the system. So now here we have introduced the error, just like in the lattice-based cryptography. So now another concept is isogeny-based cryptography. So isogeny-based cryptography, isogeny is derived from the elliptic curve only. But for this isogeny-based problem, you should have a good knowledge of elliptic curve cryptography. Not elliptic curve cryptography, especially theory of elliptic curve. Okay, so in the isogeny base, isogeny, what is isogeny? Here isogeny is mapping. A map from one elliptic curve to second elliptic curve, which is said to be isogeny if it is a non-constant morphism and is also a group homomorphism. So now again the mathematical concept came. Yeah. And what is the hard problem in this? Computing isogeny between two curves or some variant of this problem. So this is a hard problem. And again this is a exponential problem. So like its complexity on classical computer is p to the power 1/4 if we are taking the elliptic curve over this finite field ZP square. So it's actually you have to take the elliptic over the finite p square. So this is the classical complexity of the system is p to the power. So this is exponential, and elliptical discrete log problem is also exponential. But for the elliptical discrete log problem, we have the quantum computing algorithm, that can be used to solve it in polynomial time. But for this particular isogeny problem, we don't have that algorithm. That algorithm cannot be applied in the isogeny based system. Okay, so now we are coming to hash base. So hash, you know, hash, you know, SA function, SA family, then MD family and other things. So in this there is no mathematical problem involved, but security of hash, from the security of hash function itself, the security is coming from the security of hash function itself. But like it is here again, since the we have a global search algorithm to reduce the complexity square roots. Only that can be applied. So basis upon that, on the basis on that, we can increase the key size. So that is how this hash-based cryptography design. We have these XMS, GMS, and SPNS. These are the algorithm based on the hash-based cryptography. So, like you can see, to achieve the different parameters, they have given the what is the public key size, what is the private key size, okay, what is the size of ciphertext. So these are the size. So they have given the size because of that. Accordingly, we have to design the system. How much we can, what kind of hardware is required to do the computation and to store the public key and private key size, private key, different key size. Okay. So present application, what is the present application post quantum? Like in Google Chrome 124, user can use the crystal timer now. So now the X0 digital certificate standard is there where the post quantum algorithm candidate have been used, recommended. Then other place also like post quantum wired is this WireGuard, VPN is there using the classical mechanized crypto system. So they have started using this post quantum cryptography, but because of the certain challenges in the computation, in the key size and running time, because a lot of latency issues are coming. So people trying to resolve these issues. Otherwise, like algorithm, like few that I discussed in previous slide, they have already announced the crypto algorithm that we can consider the post quantum secure. And for the post quantum digital signature, they are still working on. They have also already started a computation for post quantum digital signature as well. You have a very rich library, like open domain library. Sage is a very rich open domain library. Okay, so this interface looks like Python, and lot of directly commands are available. You can call them and you can calculate and you can implement. So, and you can take large size, like not the small example. You can take big size. And for the small size, give answer very quickly. So if you are teaching to your student and if you want to show something like implementation of RSA, implementation of DP element, anything, so you can use Sage library. So this Pari and GP Pari is very specially meant for elliptic curve purpose. Okay. Then crypto OpenSSL is there. In fact, now Python direct library, Python crypto is there. Okay, I don't know what function they, how many algorithms they have implemented in the Python, but it is also good. This NTL library is very rich for finite field application. Like because if you are implementing elliptic cryptography on a larger way, then or other crypto library which are based on number theory or finite field, then NTL library is very rich library. Then they are open sources. So GNU, you can see the GNU MP. So this is a you can use this. You can call this library to do the large scale arithmetic operation. Large scale means when the size is very large. So they have implemented in very compact manner, like all the calculation they will do on 32-bit based on the 32 or 64-bit architecture. So that way you can perform the big operation on that. can take questions.
The RSA or this MD5 has been broken.
नहीं, आपको मैंने बताया था ना कि ऐसा नहीं है, इट इज नॉट करेक्ट। वो उन्होंने कुछ ये कहा था कि ये जो है हम ये एल्गोरिथम यूज करके ग्रो करेंगे, बट इट इज आल्सो क्वांटम एल्गोरिथम यूज करके हम पॉसिबल भी देख सकते हैं, बट इट इज नॉट करेक्ट।
तो वो फिर मतलब उनकी सिक्योरिटी ब्रेक नहीं हुई है? नहीं,
ऐसा हमारे पास वो है नहीं ना, कंप्यूटर है नहीं। ब्रेक मीन्स इफ यू हैव दैट यू कैन ब्रेक, यू डोंट हैव दैट काइंड ऑफ कंप्यूटर।